Good evening. This is our project and presentation on cancer growth. This is Brandon Polichetti.
I'm Brian Weir.
I'm Nolan Kelly.
I'm Connor Smith.
And I'm Glenn Pilla.
All right, so before we delve into the data, let's go over some intro and background on cancer itself. So cancer is an abnormal formation of cells that occurs randomly in the body. Billions of cells are created every day, and that causes room for mutations and different types of things called cancer. Not all tumors are cancerous. There are benign tumors, which are masses, but they do not spread. Cancer is actually the second leading cause of death in the United States, the first being heart disease. Cancer was not always on the second slot for leading cause of death. This could be for lifestyle changes, possible exposure to radiation, UV exposure, or different kinds of chemical exposure. Differential equations can help model these types of real world scenarios. There are many different types of cancers. As cancers could happen with any cell in the body, there could be skin cancer, breast cancer, kidney cancer, lung cancer. Obviously, some are worse than others, but these cancer cells do not respond to the typical apoptosis signal. Apoptosis is the signal for cell death. So these cells are ultimately unchecked by anything and grow and form masses, again, referred to as tumors. Differential equations can help model these different types of cancer situations as well. Differential equations relates functions and their derivatives. Differential equations relates farther than just mathematics alone. It actually has implications in physics, engineering, and as we'll see later on, medically. SIMIODE is a great software that we use in this particular cancer research project. It can help save time. It's more cost efficient than using real patients and real cancer treatments. Basically, many researchers and scientists can input information into SIMIODE, and this research can be used later on for generations to come and as reference for different types of cancer patients at different stages of being put into the hospitals and different stages of the treatment itself. Modeling growth. There's different ways to model growth, especially when it comes to cancer growth. The different ways are exponential, power law, Bertalanffy, logistic, and Gompertz curves. Cancer growth has some degree of predictability as it's placed in these different types of models. SIMIODE is a great way to look at these models in a real world implication in 3D or 2D methods. Now let's look at those individual models. The exponential model relates to exponential growth or decay, where it's continuously positive or negative. So it's not necessarily a straight line. It forms an exponential curve, either up or down. The power law model, it's used more for gels with different shear thinning, and this comes into play with the n value. As it gets closer or farther away from zero, this could tell a lot about the problem. The Bertalanffy model. This showcases a logistic curve created from a biologist named Ludwig von Bertalanffy. This is used to relate age differences relating to growth proportions. So this model is actually really interesting because it brings age into play. So based on the age of the patient or when they were first admitted to the hospital and they found out that there was cancer growth, this can tell a lot about the problem as well. The Gompertz model. This is the way that different types of biologists, physicists, scientists can look at the growth, decline of a tumor in very specific circumstances, mostly on a per patient circumstance. It's greatly beneficial when it comes to mapping out a different plan or treatment plan for that patient. And now the logistic model. So this works very similar to the Gompertz model. It differs in that it does not notably describe experimental data as well as the Gompertz model. However, down below on the bottom left corner, there is a logistic model for prediction of breast cancer, for example.
So as previously mentioned by Brandon, cancer growth, specifically the growth of a tumor, can be modeled through a variety of differential equations. The five main differential equations that we looked at in this particular project was exponential, power law, von Bertalanffy, logistics, and Gompertz models. And in this project, we looked at each one specifically and compared them to one another. First, looking at the exponential model, we were given a generalized model and solved it to find a generalized solution. This generalized solution is a function that allows us to calculate the total volume of the tumor. This is shown on the bottom left-hand side of the screen. With this equation, we plugged into Desmos as shown on the right. In the graph shown, it can be seen that as time goes on, this function goes to infinity. Although the function at its very beginning stages does a good job modeling tumor growth, it continues to increase at an exponential rate, which is unrealistic, proving that this model is essentially ineffective. Similarly to the exponential model, we were given a generalized model for the power law and computed an equation from it to calculate the tumor volume. Plugging this equation into Desmos, we found that the function also goes to infinity like the exponential model. This is unrealistic because the size of a tumor can approach an infinite value. It will eventually hit a plateau in a real life situation. In this case, there's a new term b which was introduced affecting the rate of the function that goes to infinity. Now looking at the von Bertalanffy model, we obtained different results from that of the exponential and power law models. After obtaining the tumor volume equation by integrating the model given to us, we saw that it had a graph different from the previous two models. Instead of going to infinity, it went to a specific value of a over b cubed. This graph shows that the function at the very beginning grows at an exponential rate. After it does that, it increases at a linear rate, followed by a period of plateauing. This proves that it's a good model for tumor volume because instead of going to an infinite value, it goes to an actual number. This is more realistic in a real life situation. Just like the other previous models, the logistic model was computed to get an equation that would represent tumor volume. Its graph was similar to the von Bertalanffy in the fact that it approached an actual value instead of approaching infinity. It did this by plateauing. For this reason, this also proves that this is a good model to effectively model cancer. Lastly, looking at the Gompertz model, we obtained a graph using the same methods as before, where we integrate to find the equations for tumor volume. We found that the model increases at a rapid rate at the beginning stages and then plateaus to a specific value of V naught e to the k over b. Again, since this model goes to an actual value, it proves that this model is effective since it doesn't go to infinity. In summary of these 5 different modeling methods, in a real life situation, cancer growth is modeled by a sigmoid curve, which consists of a model that exponentially grows in the beginning period, followed by a period of linear growth, topped off with a plateau. Based on our findings, the von Bertalanffy, logistics, and Gompertz models perfectly represent this, considering their graphs resemble this.
Okay, for the second part of this project, we're going to be fitting models to real cancer data. So how can we apply these models to real world examples? So for the first case, we are going to be examining a Chinese hamster fibroblast tumor cell. As you can see to the right, there's a table of data, T representing time, and at each time, V for volume of the tumor. We're going to use each model that we discussed in part 1 to determine which fits this data set the best. However, we're going to exclude the exponential and power as these aren't realistic models for real world examples. How are we going to determine the best model? Well, we're going to use normalized mean square error. We can use this by minimizing this value. We can obtain the optimal parameters A and B for each model. The table to the right shows the optimal values for A and B and NMSE. As you can see, the Gompertz model has the lowest NMSE, thus indicating it is the best model for this given scenario. We can plug in the A and B values from the table in the previous slide, and we can obtain the phase planes. The phase planes are going to show how general solution curves will be for each model. As you can see in each graph, the colored lines show different possible general solution curves. As you will notice, they all converge to an equilibrium point. For the Gompertz, this is 7.496 and 0. For logistical model, it is 0 and 6.93. And for the Bertalanffy, it is 0 and 8.13. While mathematically, the solution curves below 0 and above the equilibrium point can in fact happen. In real life, the general solution curves are only going to be in between 0 and the other equilibrium point. Looking at the phase planes can give us a good indication of how it's going to grow, the tumor is going to grow, and also shows that no matter the initial condition, as time goes on, it is always going to approach the same value, which is helpful in the research for volume, the growth of tumors.
Another good model of cancer in real life is examining the skin cancer of a living mouse rather than just a cancer line from a hamster. As you can see, the experimental data on the right, there aren't as many points. There are about 24 rather than the 45 from the last experiment. And we will discuss each of the 3 models that best describe this scenario. Now, which of these models best fits the data? As we can see, we still use the NMSE. In this case, the NMSE is smallest for the logistics, being 0.0388. The logistics model has the lowest NMSE, thus it is indicating the best model for the given scenario. Now, this is different from the Gompertz, which we saw in the last experiment. The possible reason for this is that the second data set hasn't had enough time to plateau. It is still in its linearly growing phase. The Gompertz model may have been a better model if we saw the tumor growth over a longer period of time. If we were to look at the phase planes, it is significantly different from the last set, in that before they were all converging to a single point. However, here we could see that they're all going to infinity, regardless of their initial conditions. This shows that the tumor will continue to grow regardless. This coincides with the idea that it is still linearly growing and has not yet reached a phase of plateau. Next up, we're going to try and tweak our models to see if we can have a cancer treatment aspect of it, because obviously every cancer scenario we try and treat them. So we are going to try and alter our differential equations with the term minus CV. This is a simple way of trying to incorporate chemotherapy or other drug uses, C being that constant drug supply. By finding the equilibria, we can determine the maximum tumor size while undergoing treatment and the minimum amount of C to eradicate the cancer. The relationship between A and C helps show the maximum size and the minimum drug amount in each scenario. Each has a different case. The exponential case, A must be greater than C to get your maximum case of being infinite. The power case, regardless of the scenario, A greater than C, A equal to C, or C greater than A, you will always have a maximum tumor possible of being infinite. The von Bertalanffy, the maximum will always plateau to its equilibrium point instead of going to infinity like the previous two, regardless of the scenario. The logistic is sort of similar. However, you can achieve this with A greater than C. So you don't have to waste as much drug C. It will always go to its equilibrium point. And very similarly with the Gompertz is that its maximum will always go to its equilibrium point, regardless of the scenario. Similarly, with the minimum amount of drug that will be needed to eradicate the cancer, for the exponential case, C must be greater than A, and it will always be eradicated in that case. Obviously, that is not the case in real life. For the power, C can be equal to A or greater than A to achieve eradication. However, for it to be equal to A, then it must be less than its equilibrium point. For von Bertalanffy, it cannot be eradicated regardless of the scenario, but it can get extremely close to 0 because it'll always converge to its equilibrium point. The logistics, A must be greater than C, and the initial volume must be less than its equilibrium point. And finally, for Gompertz, it is similar to von Bertalanffy in that it cannot eradicate using this model, regardless of the scenario.
After looking over the topic of cancer growth, it was concluded that each 5 of the models had different results. For instance, the exponential model determined that the amount of tumors cancer cells produce exponentially grows as the amount of time increases, which means that the maximum tumor cell size produced is an infinite number, which is really not accurate for tumor growth. Next, for the power growth model, it was determined that as time increases, the amount of tumor cells produced also increases if and only if B does not equal 1. The letter B determines the way in which the rate increases, meaning that if B is greater than 1, the maximum tumor cell size produced will be infinite. Next, for the Bertalanffy model, it best represented the destruction of tumor cancer cell. From the equation that was created, it was determined that the limit of time as it reaches infinity, the maximum size of the tumor cell produced would be 2000. Next, for the logistics model, it was inferred that the maximum tumor cell size produced is 1, having a constant rate of growth as time increases. Having a maximum of 1 tumor cell size balances the growth and decay of the tumor. Lastly, in the Gompertz model, the amount of cancer cells will rapidly grow at the start of time, but as the time increases, the volume becomes constant, and that will be shown by the equation V naught E raised to the K divided by B. And as a result, the 3 best models that represent tumor growth are von Bertalanffy, the logistics, and Gompertz, because they follow a sigmoid curve pattern, which is the pattern that cancer growth is commonly used and which is also shown in the hamster and mouse real-life examples. That is it for our presentation. Thank you for listening. If you have any questions, make sure to comment them below.